This is Messi from ECE of Section C. Today I'm going to explain this seminar of the subject called Ptsp, and today my seminar topic is properties of autocorrelation. And there are different types of properties in an autocorrelation function. Let us see one by one what are they. The first property is, let us consider the random process x of t, which is least wide sense stationary. That is the autocorrelation function Rx of t1 and t2 in different time intervals. It is a function of only a time difference, which is tau. The tau is t2 minus t1. Then the following properties of autocorrelation function x of t are: number one, the first property is the mean square value of x of t. So we have to find the mean square value. The notation for mean square value is e of x square of t. So e, which is e of means expectation of x square of t, is equal to rxx of 0. We have to prove this statement, and now the proof is, as we know that rxx of tau is equal to expectation of x of t and x into x of t plus tau, which is a different time interval. So if we take tau as 0, rxx of 0 is equal to e x of t into x of t, where the tau becomes 0, which is equal to e of x square of t. Hence the first property is being proved. Here this is the second property. The second property is mod rxx of tau is less than or equal to rxx of 0, where the autocorrelation function of a time difference is less than the autocorrelation function at origin or at 0. So let us see the proof. Consider two random variables x of t1 and x of t2 at different time intervals of original x of t. Here, as we have told, defined at time intervals t1 and t2 respectively, take a positive quantity, which is x of t1 plus x of t2 whole square, which is greater than or equal to 0. So take the expected value, which is expectation. Take the expectation on both sides. So left side, if we take the expectation, we get e of x of t1 plus or minus x of t2 whole square, and in the right side, expectation of constant becomes constant, so 0. Next, expanding the square, we get a square plus b square, as we know, x of t1 plus or minus x of t2 whole square, as we have we expanded the equation. After we expanding the equation, we have to simplify with the separate uh, variables. So e of x square of t1 plus e of x square of t2 plus or minus e of, as 2 is constant, it comes out, and expectation of x of t1 and x of t2 greater than or equal to 0. So from the earlier result, we have known that e of x square of t is equal to rxx of 0. So in the place of e of x square of t1 and x square of t2, we place rxx of 0. So as we have placed 2 rxx of 0 plus or minus 2 rxx of tau is greater than or equal to 0, we get this notation, and the 2 becomes constant and goes to the right side and becomes 0. And next, here this rxx of tau goes to this side, and if it goes this side, it gets minus, which is greater than or equal to 0 gets minus, and it becomes less than or equal to 0. So last we get the equation as mod rxx of tau is less than or equal to rxx of 0. So here we have to prove that rxx of tau is an even function, which is rxx of minus tau is equal to rxx of tau. So let us prove the equation. As we know, the formula of autocorrelation function rxx of tau is equal to expectation of x of t into x of t plus tau. So in the place of tau, we keep minus tau, it becomes the equation becomes as we see here. And also let us take mu is equal to t minus tau. So by the differentiation we get d, as we take tau to that side, we get t is equal to mu plus tau. So here rxx of minus tau is equal to expectation of x of u plus tau, as we have taken that t values, and into x of u. So here this equations is seen as the same equation of autocorrelation function, which is in terms of u. So rxx of minus tau becomes rxx of tau. Hence the statement that rxx of tau is an even function is been proved. And here the fourth property is, if a random process x of t has a non-zero mean value, expectation of x of t is not equal to 0 if and ergodic with no periodic components. If this all occurs, then limit mod tau tends to infinity, rxx of tau is equal to x bar square, which is mean square. So let us prove this equation. Let us consider a random process x of t, and which are in time intervals t1 t2, which are x of t1 and x of t2, and given the mean value is not equal to 0, then we take the normal autocorrelation function rxx of tau. Since the process has no periodic components, then tau becomes infinity. So let us write the equation. Limit tau tends to infinity, rxx of tau is equal to expectation of x1 or x of t1 into expectation of x of t2. So as we know that expectation of t is equal to expectation of t1 is equal to expectation of t2 is equal to x bar. So in the place of expectation of e of x of t1 and e of x of t2, we keep x bar. So x bar into x bar becomes x bar square. So hence the property is being proved. The fifth property is, if x of t is periodic, then its autocorrelation function is also periodic. So let us see the autocorrelation function, if it is periodic or not. Proof. Consider a random process x of t which is periodic with period t naught. Then x of t is equal to x of t plus or minus t naught, or x of t plus tau, which is which we take in a different time interval, is equal to x of t plus tau plus or minus t naught. So here we have the formula of autocorrelation function. Then rxx of tau plus or minus t naught is equal to expectation of x of t into x of t plus tau plus or not plus or minus t naught. Given x of t is Whiteson stationary, rxx of tau plus or minus t naught is equal to expectation of x of t into x of t plus tau. Here rxx of tau plus or minus t naught becomes rxx of tau. Therefore, rxx of tau is periodic. And here comes the sixth property. If x of t is ergodic, which has zero mean and no periodic component, then the limit tau tends to infinity, rxx of tau becomes 0. Let us prove this statement. As we have seen in the so in the second property or the third property, limit tau tends to infinity, rxx of tau is equal to x bar square, which is mean square. So where x bar is a mean value which they given as 0 mean, so x bar is equal to 0, the limit tau tends to infinity, rxx of tau becomes 0. So this is the easy property and logical property. And the seventh property is, the autocorrelation function of a random process, which is rxx of tau, cannot have any arbitrary shape. It doesn't possess any arbitrary shape. So let us see why. The autocorrelation function Rxx of tau is an even function of tau, as we have seen in the so in the fourth property, Rxx of tau is equal to Rxx of minus tau. So it is an even function and has minimum value at the origin. Rxx of tau is also related to power density spectrum through the Fourier transform. The form of spectrum is not arbitrary. Hence, the autocorrelation function also cannot have an arbitrary shape. Then here there is a property. If a random process x of t with zero mean has the DC component a as y of t is equal to a plus x of t, then the equations come here. Ryy of tau is equal to a square plus rxx of tau. So let's prove this equation. The proof is given the random equation or a random process y of t is equal to a plus x of t. Let us write in the correlation autocorrelation function Ryy of tau is equal to expectation of y of t into y of t plus tau. In the place of t, in the place of y of t, we substitute the value a plus x of t. As we have substituted, these two are separately, they were multiplied, they were expanded, the equations are expanded and written with separate expectations. And here, as we have know that expectation of constant, it becomes a constant. So e of a square becomes a square. Expectation of x of t, expectation of x of t becomes 0, as here they said that mean is 0, so expectation of x of t becomes 0, and x as well as x of t plus tau, the mean becomes 0. And here expectation of x of t into expectation of t plus tau, which is autocorrelation function in x, so we have written as rxx of tau. So the total equation becomes a square plus rxx of tau. Hence, the above equation has been proved. So, this is the last property of autocorrelation function, which is if the random process z of t is a sum of two random processes, which is x of t and y of t, that is z of t is equal to x of t plus y of t, which let us consider it as a random process, then Rzz of tau is equal to Rxx of tau plus Rxy of tau plus Ryx of tau plus Ryy of tau. So we have to prove this statement. So the proof is the given random process is z of t is equal to x of t plus y of t. Next for z we have to find out a correlation function. So Rzz of tau is equal to expectation of z of tau, z of t plus tau. So let us substitute the above equation, given equation into the z of t, and by expanding everything, by expanding every variable and giving it as a separate expectation, so the last equation we get is Rzz of tau is equal to Rxx of tau plus Rxy of tau plus Ry of tau plus Ryy of tau. So these are the properties of autocorrelation function. So in this seminar topic, we have learned about the different types of properties of autocorrelation function. Thank you.